the next around about 60 minutes, I will give you a demonstration about RFEM 5 using our add-on modules for concrete design. Therefore, I will create a foundation slab and do the design with the add-on module RF concrete surfaces. Before I start with the program itself, I will give you just a quick overview which topics I will handle in this demonstration. So at first I will show you a steel hull, which is the basis for my today's presentation. This steel hull gives me support forces for which I will do the design. Then I will tell you something about modeling in RFEM using a DXF background layer. We will take care about the supporting of the surface model, also about the load case definition and load case import or load import. I will tell you something about possibilities to define your FE mesh settings or optimize your FE mesh settings. Then we will create load combinations or result combinations for the determination of the internal forces and later for the design. And of course, at the end of this presentation, we will switch to the add-on RF concrete surfaces and determine the reinforcement which is required or would be required for this foundation slab. So I will switch to an RFEM model, this mentioned steel hull, and what you basically see here is a finished steel structure which gives me results in form of support forces. And now I want to design a foundation slab for this steel hull. And on this step, the question appears whether I should create this slab in this file or whether I should create a separate file or a separate model in which we have only the foundation slab. So both possibilities can be done with both options can be realized with RFEM. If I would model the foundation slab into this file, then this would have the benefit that I do not have to export and import the support forces and reactions. It would be completely in one file. The downside would be a little bit that I have to I have a longer calculation time, for example. So if I would change something, let's say on the girder or something on the column, I would also lose the results for my foundation slab. So if I separate these structures, the steel hull with the foundation plate into two individual files, then it have the benefit that the calculation time for each individual part of the structure is not so long. So in my case today, I have decided that I want to work with two separate files. So this is my basis for today's presentation. And I will use the support forces here on a further model with the foundation slab. Some of you maybe know the function that we can export support reactions as a load into a new file. That would be possible if you have just slabs, but in this file, or in this case, I will not use this function here because this function does just consider vertical forces. Due to the fact that I have here rigid supportings at the footings, we have also moments, and I will also consider here some horizontal forces, and these horizontal forces and moments are not considered if I use this function. Therefore, I will show you further option which could be realized by using an Excel sheet, but I will show it to you in some minutes. So as I said, this is the basis for my foundation slab. Next, I will switch to an RFEM, to a new file in RFEM. It's an empty file, and into this file we will create our foundation slab. One possibility would be to use the usual grid here and create here some lines and fill these lines with surfaces. A further option would be to import an DXF background layer, which we can use to create our slab, and that would be the first step I want to do. So therefore, I go into the File menu on the Import function, and here you see an option for DXF file import, and if this one was selected, we can also check on this option here, import as a background layer, and then the important check is into existing model. So we have already an existing model, and into this existing model I want to import a background layer. The next setting would be to check this orientation of the coordinates. That is predefined in my case. And if I hit now the OK button, then the dialog pops up where I can select my DXF background layer. That is the foundation slab in this case. I confirm it with OK, and now the interface imports this background layer here. After importing this background layer, I do not need this grid points here anymore. So on the bottom edge of the window, you can deactivate now here the grid here, and also here the snap function for the grid. So if I create now new lines, I have just activated the object snap for the background layer. The background layer can be also found here under the guide objects. We have now here the background layer, and that is the background layer for my foundation slab. May you wonder how the foundation slab look like? So I would just give loose some words how the foundation slab should be designed. So in this points here, there will be the columns assigned, or the resulting support forces from the columns. So on these points, we have our column footings, and here I need a thicker foundation slab. So I have done some kind of pre-design, and I need at least 1 meter thickness on these parts here to make sure that my embedded parts can be assigned into the foundation slab. Then we have this strip here, and there I will use variable thickness for the surface. And on this edge we will have 1 meter, and on this edge we will have 40 centimeters. So this thicker part of the foundation plate is just below the columns, and on the rest of the structure we have 40 centimeters of thickness for the foundation slab. So with this information, I can start with the modeling. At first, I will check my material. We have got here this concrete grade C2530. It's pretty fine in my case, so I will leave the material as it is. And I will start the modeling process in this part of the structure. So I will create a new rectangular surface with a thickness of 1000 millimeters. And now I can use the object snap for the background layer and can arrange my surfaces very quickly. This is my part of the structure where we have this 1 meter, and here I want to introduce a stiffer plate just to avoid singularities during the internal forces calculation, and later also in the concrete design add-ons. Therefore, I assign here an opening. So to make it a little bit better in the visibility, I switch to the wireframe display model and I create here a new opening. And if I switch back, you see here this opening, and this opening will now be filled with a new surface. And therefore, I switch the stiffness type into rigid. So after changing to rigid, you do not need to enter any thickness because it's a rigid, stiff plate. And I will assign it here. And this stiff plate is just given here for distribution of my internal forces, not in one point, but here over this small surface. To have a node on which we can assign our support forces or our loading, I have to enter a node here, this one, that is in the middle of this rigid slab. And on this node, we will assign our loads later. Next step would be to model our surfaces with these variable thicknesses. Therefore, I created first some boundary lines here. So, and now I can click once again on the function for creating a new surface. I switch back to the standard stiffness, and now I have to switch here to the variable thicknesses. And there I can define a thickness of 1000 by 1400 millimeters. And now I have to tell the program where it should assign the thicknesses on which nodes. So I can hit this button here and select these three nodes. And then I can select all the surfaces. I do it also in this case here. Open this slab once again and define also this edges or these nodes here. So we've got here 1000, here 1000, and here 400 millimeters of thickness. So to check my entries, so my definition of the variable thicknesses, I could switch to the display navigator. And at the end of the display navigator, you find an option here, colors in graphics according to, and there you can choose the surface thickness. And what happens now is that the colors on the structures will change. So you will get an info about the rigid surfaces here, the surfaces with a constant thickness. And there you see this rainbow colored diagram, which shows us that we have 1000 millimeters on this edge and 400 millimeters on this edge. So this function here is pretty handy if you are working with several different thicknesses and also with variable thicknesses to check the assigned thicknesses graphically in your structure. For the further process, I will switch back to the standard colors, and now we'll take care about this here. So once again, I create here a rectangle surface with 1000 millimeters. Once again, the opening, the rigid slab or plate, and one node. And then I just click here on these lines and this here. Okay. Now I will assign once again a surface with a variable thickness. The program has still the entries stored, so I can just click on these nodes where the thickness should be assigned to. Confirm it once again. Okay, so the rest of the part or of this foundation can be done by the mirror function here. So I will select this part and this surface. Then I can press here this button for this mirror function, create a copy, and here I have to select on which mirroring plane I want to use. In this case, it is the XZ plane, and I have to select this mirroring plane here on this point, confirm it with OK, and then we get this part, and now I just fill here the surface or this boundary lines once again with an variable thickness. Okay. Next step would be to copy this part on the right side. Therefore, I just connect here these nodes with lines, and with this activated command I can also create these lines and this one here. Okay, after mirroring I can once again or before mirroring I can once again check my thicknesses. So it still looks pretty good. So we went back here, select this, and say, here mirror, create a copy. Now I have to change the plane into YZ, and the first point is here on this point. Can copy it. And now I have all these parts of the foundation slab with the thick and variable thickness entered, and also my boundary lines. And I can use this function here and create the rest of the slab by using 400 millimeters. And now I just have to click on these boundary lines here to tell the program where it should arrange our foundation slab. Okay. Now I just press the Control and S key to make sure the state which we have now created will be saved. And the next step would be to assign here a supporting for this surface. Therefore, I can just select all the surfaces, do a double click on it, and in this tab, support and eccentricity, you can assign here a support for all these surfaces. And I have to enter here now the springs. In the first step, I would enter here as a vertical or as a horizontal spring, 5,000 and 5,000 as a value, and as a vertical spring, I will enter 54,500. To the value exact, to the value which I have designed, I will show you in a minute some comments. Though that is my default setting, let's say default setting here. I will assign it to my surface. And what I have now entered is basically a subgrade reaction modulus method. So basically you just assign a spring, a vertical spring on every FE mesh node. The benefit of this is the results are, let's say, for practical use, okay. The calculation time is not as big if you use this subgrade reaction modulus method. But the downside is that you do not consider these areas outside of the slab. So that is maybe not as accurate, so we can do here some optimizations on this supporting, how we can consider the soil model also outside of this slab. And therefore, we have several options in RFEM, and to show these options to you, I would like to switch onto our website to one knowledge base article. So in this knowledge base article, comparison of different soil models using RFEM, you find several steps of modeling. So the first step would be basically the same what we have entered now in our RFEM model, just assigning here vertical springs. So that would be a subgrade reaction modulus method, basically. And as I mentioned, the downside is a little bit that you don't consider this soil outside of the slab. One method in which you would do a little bit of optimization for this would be to assign a stiffer springs here on the edges, and you could use these dimensions here. So let's say 25% of the whole width, and use here a linear gradient for the stiffness, and increase the stiffness of the springs here on the edge or to the edge of the surface. That method is pretty handy, of course, but the downside is for this method that RFEM cannot enter a variable spring constant for the surface. So it's always for one surface, one spring constant. That would mean if I would do so, I have to divide my slab into different stripes and assign different springs here on every strip here on my foundation. So that would be time intensive, of course, and after that, in the design progress, we have to deal with several small surfaces, and that is maybe not so handy. Therefore, I would like to show you also a further option in which I assign, in addition to my surface supporting, line supports and supports on the corners. And these line support on the edges and on the corners should basically simulate this stiffness here, and it's easier in handling compared to the first mentioned method. So in this article we have also a comparison between the classic subgrade reaction modulus method, that would be the state which I have now entered in my structure, then the modified subgrade reaction modulus method with the springs on the edges, and in comparison also our add-on module RF soilin, which is using the stiffness modulus method. That is, of course, maybe the most exact option you have, but it's the downside that it's more time intensive in calculation, and I do not handle this module in today's demo. So I will use a modified subgrade reaction modulus method, basically this one here, and here on this results in this knowledge base article you see also that the results are pretty the same, so we can use this model here in our example. If you are interested in, or if you are dealing with slabs in your practical work, daily work, then I would give you the advice to take a look at this knowledge base article. You just have to make a small note for using this ID here, 001400. You can also just enter here this ID and you will directly find this technical article. Or my colleagues have also prepared a webinar 2 months ago in which they have just handled all the possibilities regarding soil models, and you can find this webinar here on our website. You just have to go here under support and learning under our webinars, and if you scroll down a little bit, then you find here soil structure interaction in RFEM. Click on that link and you will find this older webinar from October this year. And if you press on this link, you can directly open the recorded session on YouTube. And if this is interesting for you, I would give you the advice to take a look at this one here. In my example today, I will use all the spring constants here from this example. So as I mentioned, if you want to know where these springs are coming from, then just open this knowledge base article on our website. Okay, with this information, I will go back to my RFEM model. So as I said, we have entered just the vertical springs on my surfaces. I have to modify or to enter also the shear springs on my surface supports. Therefore, I open the existing surface supports. And these values are, as I said, taken from this knowledge base article, and I will also add here this shear springs from this article. And I will add here now the line supports on the edges, as mentioned before. After selection, I just do a double click on the line, click here on support, and create a new line support in which we have just a spring, a stiffness of 6055. And on the corners here, I will add here a vertical spring. And the value is 336. Okay. So these are my settings for the supportings. As I mentioned, if you are interested in these topics, just head on over to our website and take a look at this article for further information. The next step would be to save this state and to take care about the FEMesh settings. For the FEMesh settings, I have at first to do a first attempt and check what the program offers me. So I switch to the wireframe display model to make the FE elements better visible. Then I click here on calculate and click generate FEMesh. And in general, it looks quite good, I would say, but maybe we can say that in the bigger slab here, we have small elements which are not required maybe with this size. And here, where we have our thicker foundation slabs, I would like to assign maybe smaller elements to have here better results here under our columns. So therefore, I would at first change the general settings for the FEMesh. You can find them on in the calculate menu and then in the FEMesh settings. And by default, it is set to the FEMesh target length is set to 50 centimeters. And I will change it here for this example to 1 meter. Regenerate this mesh after OK. And now it looks better for the slab itself, because I do not need such a high amount of elements to get good results for the slab. Though the target length of 1 meter is okay here, but for the slabs below the columns or the thicker parts below the columns, I will work now with FEMesh refinements. So the FEMesh refinements are settings for each individual slab, and therefore I can use the Views navigator to create visibilities with surfaces which I want to handle with FEMesh refinements. So at first, I will just create a visibility for the surfaces with a thickness of 1000 millimeters. That are these surfaces. I can do just a selection of the surface and a double click. And then I can go to the FEMesh, activate here the FEMesh refinement, and on these parts I will use 30 centimeters for the FEMesh refinement. And after assigning this FEMesh refinement, you see here this symbol, which gives you already an info about the target length before you create the mesh itself. I deactivate or I cancel this visibility mode once again and select now these variable thicknesses. Select all these surfaces. Do also double click on it. And there I want to work with a further FEMesh refinement of 15 centimeters. And I can assign this to the surfaces with a variable thickness. And the last part would be to select all plates with this rigid stiffness. I select them, and then I do a double click not on the surface but on the line, on the boundary line of these rigid surfaces, and I assign a FE mesh refinement just on the outer line of these small rigid slabs or surfaces. And in this case, or in this example, I want to use 10 centimeters for the FE mesh refinement. And also in this case, you see here these little nodes. Yeah, this is the info for you about the target length, which you will receive after generation of the FE mesh. I will cancel this visibility mode. And in the display navigator, I will deactivate this symbol for this FE mesh refinement. And now we can create the FE mesh once again. And now it looks like this. So in the larger part of the slab, I'm using a target length of 1 meter. And in this parts of the structure where I want to have more detailed results and I need smaller target lengths, I'm using these FE mesh refinements. With these settings, we can start with the loading. So at first I have to create load cases, and these load cases will be filled with the support forces from my origin RFEM structure, from my steel hull. If I switch back to my steel hull, then we can check which load cases I have to consider. I've got here self-weight imposed loads, snow loads, and wind loads in all 4 directions. So basically, these 7 load combinations or cases should be considered also in my file here. Therefore, I create here new load cases. So the first one is the self-weight. Then we create the imposed load and the snow load. So and you see, if I select here this pre-installed load case description, the program knows automatically also the action combination. And this is a setting, or this action category comes in my case from the Eurocode, which was predefined in my base data from this file. I will tell you some words about this just in some seconds. So the next step would be the wind, and I can create it also in all directions. Okay, so we've got our 7 load cases. In this state, they are empty, of course, but I can already create combinations for it. So to activate the automatic combination of load cases, I do a right click on the model name and open the general data. And here you see the standard according to which I want to create the load combinations or result combinations. Now that was also the setting from our action combinations, which was predefined or preset in our load cases. In this case, or in this example, I will use the Eurocode with national annex, but it depends on you what you want to design or where your structure is, so you can select between all these national annexes for the Eurocode and also between all these standards which are given in RFEM. So all these standards are included in RFEM for the load combination. To activate the automatic combinations, I have to check on this option, and then I can select whether I want to create load combinations or result combinations. In this example, I will do just a linear analysis for the internal forces, so I can use here the result combinations. If you would have something like second order analysis or imperfections and so on, then you would have to choose the load combinations, but in this case the result combinations are okay. So the program does just the calculation of the internal forces from the load cases and combines afterwards just the result. That saves me a little bit of calculation time. So I confirm this, and if I click here now into this drop-down menu of the load cases, then you will see that the solver window pops up for a small period of time, and that is the generator for our combinations, and we've got now here our result combinations. And the result here is basically the result combination 18 till 21. So 18 is ultimate limit state. And we've got also for the serviceability limit state a characteristic, a frequent, and a quasi-permanent result combination. That is pretty fun because we can use this already like it is preset in RFEM, that you will always get these four result combinations for our add-on module concrete surfaces, also for the serviceability. But before starting the calculation, I have to fill my load cases with loads, and therefore I want to use an Excel sheet. This Excel sheet, I can show it to you, looks like this. So that are basically my support forces converted to nodal loads, and these nodal loads here, or this table, has the same scheme like my table here, table 3.1 nodal loads, and into this table I could import it via copy paste. That would be one option, or I can also copy this loading here via the Excel interface, but there's just one point I have to consider, because in my original file I have here a special numbering for the footings of the columns. So we've got here the node 101, 102 up to 106, and therefore I've got the support reactions, and then I copied the support reactions into the table in my Excel sheet, and I've got here this numbering. And now I just have to take care that my nodes in the target file have the same numbering. So that is just one topic which I have to check now. So I can activate here via right-click this numbering of the nodes. And in the display navigator, I can check which objects should be numbered here. So I don't want to see the lines, the surfaces, also not the supports and so on. So I will just I want just to make the numbering of the nodes visible, and then you see that this point here, this one here is not the 101, but it's the 9. So I have to change it individually. So therefore we have an option renumber, And then you can individually renumber the nodes, and the start number should be 101. And I just click here on this node here, it's the 101. Then we've got here the 102, 103, 4, 5, and 6. So, and now after I have renumbered all these nodes below the columns, I can import my loads from my Excel sheet. So therefore, the Excel sheet is opened in the background. I'm going to the File menu, Import, and I'm selecting here Microsoft Excel. And if I confirm this OK button, then the program is finding this Excel sheet on my desktop. And there I can activate all load cases and import them. And what the program does is basically just writing the all these tables from Excel into the tables of RFEM. So as I said, you could also do it manually by copy and paste. If I go now to the load case, for example, for the self-weight, and to the table with the nodal load, then you see here this imported loads. And we can also display them graphically. And therefore, first I deactivate this numbering. And then if you press this button here, you see all these loads here. So with this loads for every load case, we can start first calculation of the internal forces. Therefore, I would go to the calculation menu, say to calculate, and then I just calculate the result combination 18 till 21. Okay. And now we've got the internal forces. So once for the ultimate limit state, can switch not to the deflections, but to the internal forces. Then we've got also the serviceability, limit state, characteristic, frequent, and quasi-permanent. And for example, I can also switch to the quasi-permanent. And one result would be also to check whether we have negative contact stresses, for example, from the wind. And if we consider wind and self-weight, then we do not have negative contact stresses. So we have just pressure, contact pressure below the foundation slab. So with these results, we can start the analysis or the design in the add-on module. Therefore, I would switch to the add-on module itself. So in this case, it's RF concrete surfaces. If you open it, then you will get in the first mask here 1.1 the selection of the standard or the national annex which should be considered in the design. So if you order RF concrete surfaces, you have also to select a national annex or a standard which you want to use. In my case, I will use the Eurocode 2, and if you have ordered the extension Eurocode 2 for RF concrete, then you have automatically also all these national annexes available. So in today's example, I will use the national annex for Germany. Now I have to switch between these two tabs and define the loading for the ultimate limit state and serviceability limit state design checks. So at first, ultimate limit state, I'm going down here and select here the result combination. So that is my result combination, which includes all the internal forces for the ultimate limit state design. And if I switch here to the serviceability, I'm choosing here this characteristic, frequent and quasi-permanent result combinations. The next step would be to check the materials. The materials or the concrete strength class was taken from my model itself, so that is okay. And the preset of this reinforcement steel is also okay in this example for me. Next would be the surfaces, and if I switch to this table with the surfaces, then you see here some red entries. These come from not designable surfaces, and if you remember, then I have assigned there small surfaces, small rigid surfaces below my column footings, and they are of course not designable because they are rigid. And by default, all surfaces which are included in your RFEM model will be taken into account into these RF concrete surfaces add-on. So if I switch to the table 1.4, there you see all settings regarding the reinforcement are applied on all surfaces by default. And that can be changed. So I uncheck this all here, delete all surfaces, and then I can graphically just select all surfaces which have a standard stiffness and the concrete material. Therefore, I'm going to the views navigator, and then I select just the surfaces with a material or with a, let's say, standard stiffness. Then these rigid surfaces will be hidden, and I can select all these surfaces, confirm them. And if I switch back to the surfaces table, I can now activate this filter that I just want to display here, the used surface. Then also our not designable surfaces disappear here in this table. The next step would be to do here the settings for the serviceability limit state design checks. And there is especially interesting the crack width control and also the AS-min due to effects to restraint by for drain of hydration heat. I will leave the detailed settings or the standard default settings here for the crack width control. So I will do the crack width control with an indirect calculation and with a direct calculation, and the program will automatically choose the design checks which leads to the most economical reinforcement. And the crack width I want to check is 0.3 millimeters. So that is the setting for my crack width control. And here on the right side, we find the settings for our minimum reinforcement due to the effects of restraint from drain of the hydration heat, in this case for this foundation slab. So drain of hydration heat would be in this case a pure tension restraint. So I change it here to this KC factor 1.0 for all the surfaces. So the program would now calculate the minimum reinforcement due to this restraint effects for pure tension. and it would assign here a FCT effective to FCTM, and you can also modify this. So as I said in the first part, in the first table, I will use the German national annex, and in the comments of the German national annex, we can find a recommendation how we can reduce this FCT effective if we say the crack formation happens in the first 28 days. So I will activate this option here, and I can work here with reduction factors for FCTM according these recommendations in the German annex for Eurocode. These recommendations are, for example, that we can use for slabs with a thickness up to 80 centimeters, a reduction factor of 0.75, and slabs with a thickness larger than 80 centimeters, a reduction factor for FCT effective is 0.85 times the FCTM. So I will assign these factors here for the determination of IS-min to all the surfaces, and this should affect here FCT effective. So in the first step, I will apply 0.85 for all surfaces, and you see now how this FCT effective will be reduced. And for the slab, for our larger slab, which has just a thickness of 40 centimeters, we could do an individual setting, therefore. So I deactivate here this multi-selection, and I'm handling now just the surface 27 and enter here a reduction value of 0.75. So you see here for the IS-min calculation, I would use FCT effective of 1.95 for this surface number 27. That is, as I said, our bigger slab with the 40 centimeters, and all other slabs are using this FCT effective for the IS-min calculation. As I said, these are recommendations from the National Annex of Germany. If you have other recommendations or maybe other literature where you can find information for changing this FCT effective, then this is the setting in the program where you can enter it. Okay, after definition of the settings for the SLS design checks, I will switch to the reinforcement, which we want to consider here in our slab. Therefore, I switch it first into the reinforcement layout. And I have to define a concrete covering for my slab, and this should be done according to a standard, so according to our German national annex from the Eurocode 2. So I activate this check here, and if I click on this button, then I can select an exposure class for the bottom side of the slab and also for the top side. For the bottom side, I would like to use here XC2, and by default the top side has the same exposure class, but I would like to use here on the top side XC3 for the concrete covering. And if I confirm that, then the program automatically assigns the layer on the top side in direction 1, in direction 2 in the right height, and the right concrete covering. The next step would be to assign a longitudinal reinforcement for the design. And by default, there is nothing set here, but I want to consider at least a provided reinforcement of from a diameter of 12 millimeter and a distance of 10 centimeters. Therefore, I click on this button here. And as I said, I want to consider a basic reinforcement with 12 millimeters and a distance of 10 centimeters. So that is an estimated value from my side, and that is my first attempt, I would say. And I think that this should be considered at least as a reinforcement here. And I want to consider it on the top and the bottom side and in both directions. So we get as a provided minimum reinforcement here, a basic reinforcement is 11.31 square centimeter per meter. I enter this one here, and if I would need during the calculation progress also an additional reinforcement, then I will use in the first attempt the same diameter for this maybe additional requirement reinforcement. So I'm entering here also this 12 millimeters. Due to the fact that I have changed here these diameters, also the concrete covering was influenced. So I'm going back once again into this table, and there I see that we've got here different values here from the concrete covering now, and I want to use the additional reinforcement, or if I need additional reinforcement, then I would like to assign it in the first attempt in the same layer as the base reinforcement. So I will add here also this 41 millimeters, and on the bottom side this 36 millimeters. So basically in my first attempt here, the basic reinforcement and the maybe required additional reinforcement are in the same layer. The next settings can be left like they are, so that are default settings from the Eurocode 2, and there you see here once again the national annex for Germany. It depends on the national annex which you have selected in the first mask, which values you see here. Yeah, that are basically recommendations from the Eurocode, so you don't need to change them by default. With these settings, I can start the calculation process. So the first point is, or the first step is that the program calculates the internal forces for the selected result combinations. Then it would calculate the required reinforcement for the ultimate limit state. And then the program checks on every FE element whether the what is the max value, the defined basic or the provided reinforcement, or the required reinforcement due to the ultimate limit state design checks. And with the max value of both, the program would start the serviceability limit design checks. And if these serviceability limit state design checks are not fulfilled with the reinforcement, the program automatically increases these reinforcements. So at the end of the calculation, we should get results with our required reinforcement, which fulfills the design checks in the ultimate limit state and also serviceability limit state. Okay. The calculation is done here, and I can switch here back to the graphics, or we could use here. Yeah, I see here that we've got the design ratio of 0.1. That is exactly that what was also estimated. So the AS min due to the drain of the hydration heat and restraint is decisive here in this case. It's basically like expected. So we've got here a required reinforcement which comes directly from the AS-min, minimum reinforcement, due to this restraint. And you see these results here in the result navigator of RF concrete surfaces. So it is the required reinforcement governing of ultimate limit state and serviceability limit state. You see these values here. If you check, if you select here only the ultimate limit state, then you would see that you would need in most of the parts less reinforcement on if you would just consider the ultimate limit state. So the serviceability limit state is governing here, and we see the same result if we go to the serviceability limit state design checks here. There you find the reinforcement, the minimum reinforcement, and there you get exactly the same results here. So that is AS-min, the direction 1 on the top side and also on the bottom side. So you see this AS-min would be required, would be the most decisive part here of the result. So that point with the reduction of this FCT effective is the most decisive point in this calculation, and you have to take care how much you can reduce this FCT effective in your calculation, and you can directly influence the amount of required reinforcement with this option. One last result here would be the shear reinforcement. So we have got the longitudinal reinforcement, which was decisive from the serviceability, but what was also checked in this add-on is the shear reinforcement, and therefore it's maybe the first thing I would check is the ratio of VED to VRDC. So you would see here in which parts we've got maybe a problem with shear forces, and the most parts are, or this ratio for shear reinforcement ratio, shear force ratio is below 1. There are just these parts here where our forces from the columns are assigned on the slab. We've got, or we are getting problems here, or values above 1.0. So these parts can be handled with punching proof design checks. So these punching proof design checks could be done with RS Punch Pro. That is not part of this demonstration here, but if you want to do punching proof on this slab, you could use, or you could perform them with RF Punch Pro. Therefore, you would just need to change this rigid slabs here into slabs with, or surfaces with standard thickness. Otherwise, the add-on model cannot handle them. And with these results, I'm coming to the end of the first part, and in the afternoon, I will give you further information to this slab here regarding documentation of results from this calculation with our printout report. Thanks for your attention.